Hello everyone, welcome to Wings of Physics. Myself Dipali Kulkarni from PVP Junior College, Pravaranagar, Loni. Today we will start the new chapter, and name of the chapter Magnetic Field Due to Electric Current. Okay, let us start. In electrostatics, we studied that when a charge is there and this charge is stationary, it produces a field around it, and that field is electric field. Intensity of that field, that is denoted by a vector quantity, and that is called as vector E. Then the force in this electric field, that is given by Fe, that is equal to the magnitude of this charge and the vector E, product of Q and E, that is the force in electric field. If charge is moving, the force is same, means Fe, that is equal to Q into E. Now suppose charge is moving, means in this manner. When charge is moving, at that time current is formed, because we know that current, that is rate of flow of charge. And when this charge or electron is moving in this manner, at that time one field is also produced, and that field is a magnetic field. When charge is moving, at that time one another force is produced, or one another field is produced, and that field is magnetic field. This proves that when current flowing in a conductor, at that time magnetic field is produced, that is discovered by Hans Christian Ørsted. When a magnetic needle, suppose this is a magnetic needle that is kept near this conductor, at that time it shows the deflection. And this proves that when this magnetic needle shows deflection, this proves that current carrying conductor produces a magnetic field around it. When we change the direction of this current, at that time the direction of a needle that also reverse. This indicates that, or this proves that, a electric current flowing through the conductor that produces magnetic field around it. Then when charge is moving, suppose this charge is moving, Q charge, that is moving with velocity V, and the magnetic field produced, the strength of that magnetic field, that is denoted with the help of vector quantity, and that is called as magnetic intensity. It is also called as a magnetic induction. And when charge Q moving with vector velocity V, and a strength of field is B, at that time the magnetic force that is given by formula, Q into V cross B. Vector product of this velocity vector and the magnetic field. Then this is the magnetic force. First we will study the right hand thumb rule. What is the right hand thumb rule? Right hand thumb rule. Right hand thumb rule. Right hand thumb rule. Consider this is a conductor carrying current I. Then hold this conductor in your right hand. This is my right hand, and hold this conductor in your right hand in such a way that this is the direction of current. Means outstretch your thumb in the direction of current and curl your finger around the conductor. In this manner, suppose this is the direction of current, your thumb should be stretched in the direction of current and curl the finger in this manner. Then curled finger gives you the direction of magnetic field or magnetic intensity or magnetic induction. Then this is in this manner, this curled finger that give you the direction of B, and that is in inward direction. This is in inward direction. Means sense, this sense is anti-clockwise sense, and that direction of B, that is the inward direction, and inward direction of B, that is denoted by a cross. If we reverse the case, suppose current is in downward direction, then what happen? In this manner, current is in downward direction, curl the finger around the conductor, then this is the direction of current, and curled finger that give you direction of magnetic induction or magnetic field or magnetic intensity, and this is the outward direction. Direction of B is in outward direction. Suppose in this manner, direction of B is in inward direction. In this case, direction is in outward direction, and this is the direction of current, and B, that is outward direction, that is denoted by dot, and dot indicates that outward direction. Direction of B is outward direction. Means this is inward direction. When current is in upward direction, B is in inward direction, means into the plane, and when current is in downward direction, it is out of the plane. And what is the statement of the right hand rule? Imagine a conductor is to be grabbed in your right hand in such a way that outstretch your thumb in the direction of current, then curled finger gives you the direction of magnetic field. That is the statement of right hand thumb rule, and that gives you the direction of the magnetic field. Okay. Now we have to study the Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand rule. Consider a one conductor. Current I is flowing in that conductor and a magnetic field produced around it. When another conductor is placed here and direction of current is the same as that of the first conductor, then what happens? Then the force is there. When second conductor is present, then it apply a force on a first conductor. What is the function of field? Field चं काम काय असतं? Field apply a force. Field काय काम करते? Force apply करण्याचं काम करते. आणि म्हणून आता suppose the current is in this direction, means both the current on the conductor, they are in the same direction. Then the charge means direction of the electron is in this direction, because we know that the direction of electron is opposite to that of direction of current, means velocity vector is also in this direction. When current is in upward direction, then velocity vector is in downward direction. Okay. Now the magnetic field, when current is in upward direction, then magnetic field is in this direction, means it is in inward direction. This is direction of B, and force is in this direction. Okay. Now Fleming's right hand rule. What is the Fleming's right hand rule? Stretch the forefinger. This is our forefinger. It is also called as index finger, middle finger and thumb of your right hand in such a way that they are mutually perpendicular to each other. Understood? This is the index finger or forefinger, middle finger and thumb of your right hand in such a way that they are mutually perpendicular to each other. Means angle between these two is 90 degree. In this two is 90 degree. In this two is 90 degree. Okay. Then the forefinger indicates the direction of magnetic field. Middle finger indicates the direction of current and the thumb denotes the direction of motion of a conductor. Okay. म्हणजे हे बोट बीचं बोट मॅग्नेटिक फील्डचं बोट, हे बोट करंटचं बोट आणि हे मोशन ऑफ ए कंडक्टर. अंडरस्टूड. स्ट्रेच द forefinger, middle finger and thumb of your right hand in such a way that they are mutually perpendicular to each other. Then forefinger indicates the direction of magnetic field, middle finger indicates direction of current and thumb denotes the direction of motion of a conductor. This is Fleming's right hand rule. Okay. Now we have to study the Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand rule. Now stretch. This is the left hand. Stretch the forefinger, middle finger and thumb of your left hand in such a way that they are mutually perpendicular to each other. Okay. Then this forefinger denotes the direction of magnetic field, middle finger denotes the direction of current and thumb denotes the force acting on a conductor. Okay. परत हे बीचं बोट, हे आयचं बोट, बी मीन्स मॅग्नेटिक फील्ड, हे करंटचं बोट आणि थंब force acting on a conductor. Understood? Means these three quantities, they are mutually perpendicular to each other. Okay. And therefore the vector V and vector B, they always make some angle with each other. Means this is the field when charge is stationary and this is the field, this is the force when charge is moving. Means when the charge is stationary, at that time electric force is present on that charge, and when charge is moving, then magnetic field is present on that charge. Okay. And when an electric current produces magnetic field around it, at that time simultaneously electric field and magnetic field is present and net force acting on that charge, that is called as a Lorentz force. Means the force, that is the summation of electric force and magnetic force, and the Fe, that is equal to Q into E, then this Q into V cross B. If Q is taken as common inside the bracket, we can write E plus Q vector V cross B, and this force is called as a Lorentz force. This force is called as Lorentz force. Okay. Then later on, the Gauss, Henry, Faraday, they prove that the magnetic field is partner of a electric field. After that, the Maxwell with its theoretical work proved that many practical applications such as electric motors, generators, communication system and computer, that are the application which are based on the magnetic field due to electric current. Means this phenomenon is very, very important in our daily life. Okay. Now we have to study the consequences of this Lorentz force. What are the consequences of Lorentz force? Okay. Magnetic force, that is given by formula Q into vector V cross B. Means this V and B, velocity of a charge and the magnetic field, they make some angle with each other. And according to the vector product V cross B, that is nothing but VB, product of magnitude of two vector and sine of the angle between them, means this vector V and vector B, that should make some angle with each other, and the direction of this cross product, that is a third vector which is perpendicular to the plane containing these two vector. We already studied this concept of vector product in 11th Science, chapter number 2, Mathematical Method. The cross product of these two vector, that is a third vector, and that gives you the force, and that is perpendicular to these two vector. Okay. Then what are the consequences of the Lorentz force? First thing, when V is parallel to B, vector V is parallel to B, means, or V is anti-parallel to this B, means theta when parallel to V is, vector V is parallel to B, theta बरोबर 0 degree, and V is anti-parallel to B, then theta बरोबर 180, theta equal to 180 degree. And when we know that sine 0, that is equal to 0, or sine pi or sine 180, that is equal to 0, means when V is parallel or anti-parallel to each other, at that time this magnetic force is always equal to 0. Okay. This is the first consequence of the Lorentz force. Second thing, when V is stationary, means the velocity V, that is equal to 0, means charge is stationary, it is not moving. At that time, when this V, that is equal to 0, then force is 0, though magnetic field is not equal to 0. But when velocity of this charge, that is 0, means charge is stationary, at that time magnetic force, that is equal to 0. Okay. And when they are perpendicular to each other, V, vector V, velocity vector, and magnetic field, they are perpendicular to each other, at that time then the force is exactly perpendicular in this manner. The force, direction of force, that is perpendicular to these two vector, means angle is 90 degree. At that time the direction of force, that is perpendicular to the plane containing these two vector. Understood? In this manner, this is the consequence of a Lorentz force. Then we have to study the magnetic force in detail. We already studied that in circular motion. What happened in circular motion? In circular motion, centripetal force is towards the center of circle, and direction of velocity is in this manner. In every case, this is the direction of centripetal force and this is the direction of velocity in circular motion. Then work done, that is equal to 0, because this angle between them, that is the 90 degree in circular motion. In similar manner, in magnetic field, what happened? The direction of this force is this magnetic force, that is always towards the center of circle, and direction of velocity vector is in this manner, means they are always perpendicular to each other. And due to that, work done by this magnetic force, that is always equal to 0, because angle between them, that is 90 degree, and therefore the work done, that is the product of force and velocity. And velocity vector is in the direction of displacement vector, and therefore W, that is equal to F dot S, and if the F dot S, that is equal to F S cos 90, because in dot product of magnitude of two vector and cosine of the angle between them, and therefore work done, that is the cos 90 that is equal to 0, and therefore Fs into 0 that is equal to 0. Means work done due to this magnetic force that is always equal to 0. But what happened due to the magnetic field? In magnetic field, this magnetic force gives the direction to the field, but the speed remains constant. It does not affect the speed. Suppose speed of this charged particle that is 40 meter per second. In every case, that speed remains constant. Means this magnetic force that does not affect the speed, but it gives direction to the field, and work done due to this magnetic force that is always equal to 0. And this is the main use of a magnetic force. It gives direction to the accelerating particle, but it does not affect the speed. Speed remains constant. It does not change the speed. Who change the speed? The electric force that can change the speed, value of speed, but magnetic force that gives only direction to the field. And this is the main important function of a magnetic force that we have to study that function later on in a cyclotron. We have to use that property of magnetic force in case of a cyclotron. Then what is the SI unit of this B? In vector form, we can write this force in this manner. Fm that is equal to Q VB sin theta. This is the magnitude, and n cap that is the unit vector in the direction of this force. This is one another form of a magnetic force. We can write second vector form of this magnetic force, and theta is the angle between this V and B. Means there should be some angle in between V and B. Okay. Now we have to study the unit of this magnetic induction. Then B, we know that F, if the angle between them is 90 degree, then F that is equal to QVB, and therefore B that is equal to F by QV. Then what is the SI unit of force? That is Newton. Then SI unit of charge, that is Coulomb. And SI unit of velocity, meter per second, it become second into meter. Means the SI unit of magnetic induction, magnetic intensity or magnetic field, that is Newton second per Coulomb meter. One another unit that is called as a Tesla, that is also called as Tesla. And one another unit that is Weber per meter square, it is also called as Tesla. Okay. Now we have to define 1 Tesla. When a 1 Newton force, this is 1 Newton force, acting on a 1 Coulomb charge. Suppose charge is 1 Coulomb and moving with velocity 1 meter per second and perpendicular to magnetic field. At that time, magnetic induction is 1 Tesla or 1 Weber per meter square or 1 Newton second per Coulomb meter. Okay. When a 1 Newton force acting on a 1 Coulomb charge with a velocity of 1 meter per second perpendicular to the magnetic field, then the magnetic induction is 1 Newton second per Coulomb meter or 1 Tesla or 1 Weber per meter square. Then we have to obtain the dimension. But before that, one convenient unit of a magnetic field, that is Gauss, and relation between Tesla and Gauss, that is 1 Tesla that is equal to 10 raised to 4 Gauss. Gauss is convenient unit, and this is the relation between Tesla and Gauss. Now we have to obtain the dimension of this B, dimension of force F that is equal to ma, mass into acceleration. Okay. So m raised to 1, L raised to 1, T raised to minus 2. That is the dimension of force. Then dimension of Q, current, that is nothing but rate of flow of charge, means Q that is equal to IT. Means T raised to 1 and ampere raised to 1. And velocity means L by T, m raised to 0, L raised to 1, T raised to minus 1. That is the dimension of velocity. Then total dimension, okay, this L raised to 1, L raised to 1 that gets cancelled, T raised to plus 1, T raised to minus 1 that gets cancelled, okay, and total dimension L raised to 0, m raised to 1, T raised to minus 2 and ampere raised to minus 1. That is the dimension of the magnetic field or magnetic induction. In this manner, we will study the electric force, magnetic force, Lorentz force, then the direction of this B, V and F. Okay, I hope all of you understood this concept very well. Thank you for watching this video. If you like this video, then like, share and subscribe my channel. Okay, thank you.